All right, we're going to talk about two things. First thing we're going to talk about is inductive. Oops, I got to change a couple things here. There we go. Okay, we're going to talk about two words, inductive reasoning and deductive reasoning. Let's talk about deductive first. Deductive, that's supposed to be a U, looks like a V. Now that's a V. Deductive reasoning. I won't do a whole lot of writing up here, but so we'll do a little bit of reading in here. Let's talk about deductive first, because inductive's a little bit more lengthy. But look at the bottom of page 54. You see the 54? There's a big old paragraph. See that big fat paragraph, bottom of 54. Towards the bottom of it, about 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5 lines up, it says deductive reasoning. It's in bold. Let's read that real quick. It says deductive reasoning is the process of using a rule once it's been formulated. So basically, deductive reasoning is if they tell you that something is true, then, and you look at it, for instance, let me think of a, just trying to think of something off the top of my head here that I can use that you might be familiar with as far as deductive reasoning. Well, I can't really think of a good deductive reasoning, but if they tell you, I need to think of some kind of example here. So we have something says in geometry we're covering this. If you have two lines, if you have parallel lines, so if you have parallel lines, then actually, if you want to write it all the way out, I'm not going to. But if you have two parallel lines cut by a transversal, then the let's say alternate interior. Do you remember that from geometry? Alternate interior angles. We did it in here actually, didn't we? In one of the lessons. Yeah, the alternate interior angles are equal. Okay, so watch. If I had two parallel lines, right, and I said here's angle 1. I tell you what, let's make this, let's say that's 31 degrees, and I said solve for x. All right, and so when you look at this, these two lines are parallel to each other. What is x equal to? It's 31, right? Why is it? What reasoning? What did you base your answer on? Well, you didn't base it on, well, I think, it's going to be this. I based it on something that's actually written out specifically. It's specifically written out that if you have parallel lines cut by a transversal, then the alternate interior angles are going to be equal. You look at these two angles. Those two angles are alternate interior angles, and so they're going to be equal to each other. What did you base it on? What was your reasoning behind it? Well, my reasoning was this thing right here, this theorem, this alternate interior angle theorem, told me that that was true. That's what I based it on. It's something that's already been established. It's something that's already been written out, a rule. Okay, that's deductive reasoning. Do you follow me on that? We use deductive reasoning a lot. Okay, stuff that's already been established, we come up with a logical conclusion, right? Our conclusion is what? Our conclusion is that x equals 31 degrees. What is it based on? It's based on this theorem. What kind of reasoning did we do? We did deductive reasoning. So that works out. Does that make sense? What about inductive reasoning? It's a little bit different. It's not so clear-cut. Inductive reasoning. Let's see, they do a flipping the coin. All right, let's say this. Let's use their example, and I'll give you another one as well. Their example is you start flipping a coin, right? You flip a coin, let's say we flip it 100 times. Well, it comes up heads 40 times, and it comes up tails 60 times. All right, you follow me? So we did it 100 times. I mean, that's a lot of times. It's not like we just flipped it twice, or we just flipped it once, and we said, well, let's flip a coin, comes up heads. What does that mean? Oh, it's going to come up heads every single time. Is that what it means?
Nope.
No. That's an actual way of reasoning inductively if you do that. But let's say you flip it 10 times. All right? Let's say 9 times it came up heads. Does that mean that the next time you flip it, it's definitely going to come up heads? I mean, you got a 90% chance, right? No. What if you do it 100 times? You flip it 100 times. 40 times it comes up heads, and 60 times it comes up tails. Does that mean that it's always going to come up tails 60% of the time compared to 40? No, it isn't. I could flip it 1,000 times, and my numbers might be a little bit different. Think about it. The more you flip, the more you flip. Let's flip it 1,000,000 times. What do you think it's going to get closer and closer and closer to? Is it going to be higher for heads and lower for tails? I mean, tails never fails, right? That's what I always say when they flip a coin. I say tails never fails. And is that always true? No, it's not always true. It's a funny thing to say, but it's not necessarily true. So what happens? Let's say I flip it 100 times, 1,000 times, 10,000 times, 100,000, 1,000,000 times. What do you think my percentages are going to start to be the more times that I flip it? What do you think? Yeah, even it out. So what? 50-50, right? Yeah, 50-50. And it's exactly what's going to happen. That's inductive reasoning. Now, does that mean you flipped it 1,000,000 times, right? Let's say it came out, 1,000 more heads than tails. Does that mean the next time you flip it, you're going to get a head? No, you could get a tail, couldn't you? All right? You follow me? That's inductive reasoning. And it's it's not the greatest example in the world, but that's kind of the reasoning. Here's an example that I just kind of made up. One year when I taught this. Let's say you're at the Longwood Gardens. Okay, this is it's like a I don't know, what would you call it? What is it? It's like this place they actually pay to get into it, Mark, and you get they got all these flowers and all kinds of stuff. It's like a garden, a big huge garden. Is that what you said?
He said theme park.
Oh, theme park? Not exactly a theme park. It's not that fun. I mean, if you like flowers and if you like to sniff the flowers, then it's a nice place. Anyway, you go there. So here's my example. This is inductive reasoning. You follow me? Watch this, right? Here's inductive reasoning. You walk by a certain flower. Okay, let's say the roses. We'll say you walk by the roses and you're fine. You're having a good day. Everything's good, and you start sneezing like crazy. You just start sneezing, right? And then you walk to the next flowers, something else, to the sunflowers or whatever, and you quit sneezing, and you're fine. Like, oh, that was weird. And you're like, oh, I forgot something back there at the roses. You go back to the roses, and guess what? You start sneezing again. So what would you reason? What do you think the reason for your sneezing would be? Probably the roses, right? Maybe you're what to the roses? Maybe you're allergic to the roses. Maybe there's something in those roses, okay, that's making you sneeze, and you're allergic to the roses. That's inductive reasoning. Is that necessarily true, though? No. Did you get a blood test done and sent to the lab and they told you, yes, you're definitely allergic to roses? No. That would be deductive reasoning, all right? Something that's already been established. Inductive reasoning would say, okay, I think I'm allergic to these roses. But that might not necessarily be true. That's not always the greatest form of reasoning. Give me another reason why maybe you started sneezing. Maybe you weren't allergic to the roses. What do you think? Give me another option.
Maybe something in the air.
Yeah, maybe, I don't know, maybe there's some old lady with some nasty perfume, right, on that she was standing by those roses the whole entire time, right? And maybe you're allergic to her perfume. You never know, all right? It could be all kinds of reasons, right? It might not just be that you're allergic to those roses. You follow me? But your reasoning was what? I walk away from the roses, I don't sneeze. I go near the roses, I start sneezing again. So you induce, right? Your reasoning, you induce that, okay, I'm allergic to these roses. All right, that's reasoning. Okay, sometimes it's correct reasoning, and sometimes it's incorrect. It's false. Sometimes it's true reasoning. You may very well be allergic to those roses. Okay. Another example of inductive reasoning would be like we were talking Phillies a second ago. What if you're batting, right, and a pitcher comes up, and well, the pitcher, they always do. They always have these charts on batters, don't they? Especially in the pros, right? And they say, all right, this guy likes the ball high and inside. So what's the pitcher going to do? Is he going to pitch it high and inside? No, hopefully not. If he's trying to get the guy out, he'll probably low and outside or something like that. Okay? Yeah, and try to do that. So he reasons because what's on that chart? The reason is most of this guy's hits are when the guy pitches high and inside. He's getting a hit or he's getting a home run. So you reason inductively. Now, does that mean you could not strike him out with a high and inside pitch?
No.
No, you still could, couldn't you? All right, but you reason inductively. That's inductive reason, okay? It's basically circumstances. It's a compilation of a bunch of circumstances that happen, and you're like, oh, it happened this many times, this certain way, so guess what? The next time I get in that same circumstance, it's probably going to happen again. Does that make sense? But what's the key word? It'll probably happen again. Does it mean it necessarily will? No, not necessarily. So that's inductive reasoning. All right? So that's just the difference between deductive reasoning and inductive reasoning. All right? Just try to remember those examples. All right? What we're going to do today is talk about a couple things. I'll write another word down. This thing is called a syllogism. It's kind of weird. S-Y-L-L-O-G-I-S-M, syllogism. And these syllogisms, I'm going to show you one. There's two parts to a syllogism. One is the major premise. Major premise. And the other is the minor premise. You figure that was coming, right? After major. And then you have a conclusion. I'm going to put a line right here because this is how they write this. The first line is the major premise, the second line is the minor premise, and then the third line underneath of this, okay, line's kind of like an addition, looks like an addition problem kind of. They call this the conclusion. What we're going to do, we're going to make some what do you call it? I don't know what I'm trying to think of. I'm trying to come up with a conclusion from these things. Let's just start with an example. I don't like the first example. Well, yeah, let's use it. What the heck? All right, watch this. Aristotle. Remember, the first line is the major premise. So, oh, I'm sorry. I'm not going to do the Aristotle thing. I am going to do that. But right, all men are mortal. So this is our major premise. Okay. Now, whether this is true or not, it really doesn't matter. All we're trying to do is follow the line of reasoning, the line of logic. Okay. We're not really going to talk right now anyway about whether this is true or not. But it says all men are mortal. Let's just talk about that for a brief second. Is that necessarily true that all men are mortal? Well, all men now are mortal. Have all men in history been mortal? No, there's been one, right? If you believe what we believe, right? There's one, Jesus Christ. He was not mortal, okay? So that statement's not necessarily true, is it? But I don't care about the truthfulness of the statement. I just want to follow the logic, okay? We're just looking at logic right now. So if I give you the statement, all men are mortal, just take that as an accepted fact, okay? Look at the next sentence. It said, Aristotle is a man. Or, I'll tell you what, Aristotle. Let's just say Bob. Okay? So Bob is a man. What we want to do is we want to make a conclusion. We want to conclude from these statements. Again, I don't care if these statements are true or false. Okay, I just want to see the logic in the statements itself. Just assume that what they're saying is true. Okay, so it says if a person's a man, basically is what they're saying, isn't it? So all men. If a person is a man, then guess what they are? They're mortal. Well, it says Bob's a man, so what's our conclusion then? That he must be mortal. Okay, so that's our conclusion. Bob is mortal. That whole thing that we just did right there. The top one is the major premise, the second one is the minor premise, and the bottom is the conclusion. That whole entire thing right there is called a syllogism. And what we're going to do is we're going to look at some of these things and see whether or not their reasoning is logical or not. Okay? We just want to see, is it logical reasoning? What we have, and let's stop this video and we'll go to the next one. We'll do a couple more examples like this.